Hi everyone. Today I'm here to present our paper, Conjugate Momentum-Based Thruster Force Estimation in Dynamic Multimodal Robot. This is a combined project by Northeastern University and California Institute of Technology, and it's funded by TIA and NSF. This slide shows a team of researchers who collaborated on this project. Let's start by understanding Harpy hardware. Harpy has 12 degrees of freedom, 6 for torso and 3 for each leg. Each leg consists of 3 joints, one in the frontal plane for hip abduction and adduction, 2 in the sagittal plane, one for swing at the sagittal joint, and one at knee for flexion and extension. Next, it also has 2 EDFs attached onto its torso. Using the torso pitch, we can do control thrust vectoring. Further, some physical characteristics for Harpy. Total mass of Harpy is 6.5 kg, standing height is 0.7, and it has 0.4 foot. It has 2 onboarding computing elements. One individual Jetson Odin, which gets the data from internal real sense and other visual sensing elements. And it has an STM32, which gets the data from ICM IMU. And it also has an encoder for getting the joint data. This slide shows the performance metric and the actuator details. It has a total peak joint torque of 22.5 Newton meters. The maximum thrust force per EDF is 2.5 kgf and the thrust to weight ratio is 0.76. Since its thrust to weight ratio is below 1, to perform agile maneuvers, it need to use both its leg and aerial unit together. Next, each joint is made from a custom pancake BLTC motor along with 50:1 gear ratio, and each joint is controlled by one Elmo amplifier, and combine all the Elmo amplifier are powered through 6S LiPo battery. Next, we show some initial results from Harpy, where it's performing 2D planar walking and 2D planar vertical jumping. It does so by using both its leg and aerial unit together. At the bottom, we show some gait metrics such as gait duration, forward speed, and flight phase duration. This shows the inspiration or motivation behind our current hardware platform and this current work. It shows Fido bird performing vertical high jumps. It does so by combining the effort from both the wings or the thrust produced by the wings and the legs. To do similar sort of maneuver on a hardware platform, we need first the good estimation of thruster force. Once we have this estimation of thruster force, we can then later on use it into our control unit, on our onboard control unit. So now let me walk you through some key estimation methods in the literature. And now I have organized this thing in 3 different approaches or 3 different sections. First is the momentum-based EKF. Momentum-based EKF combines the momentum dynamics with the Kalman filtering. Mohammad's work is for flying robots with thrusters, but it doesn't handle the ground contacts. Bolch and Kamuri focuses on legged robots, but don't consider the thruster force. And Warburg applied the same to manipulators. Next one is the generalized momentum observer. These observers were pioneered by Dialuca for collision detection. These methods are robust and they don't need acceleration estimate, but they were designed for manipulators and not for multimodal robots. Lastly, we have disturbance observer. Disturbance observer treats external force as a disturbance to reject. Castillo and Gove developed this for drones. Amo and Ho applied them to manipulators. Again, none of them handles the couple-legged thruster dynamics. Our work. So where does our work fit in? We first estimate the thruster force during the intermediate ground contact. Our system has coupled dynamics. The leg affects the thruster force and vice versa. And we do this without expensive force sensor. This is critical for dynamic legged aerial locomotion. So now we start with the mathematical modeling. The figure on the right hand side represents all the parameters that we use for our modeling. We find first the equation of motion by using the Euler-Lagrange method shown over here. In this, M is the mass inertia matrix, H is a combination of Coriolis matrix and gravitational vector, Q is the generalized states and Q dot is the velocities for the generalized states, UM, UT and UG are the inputs, and BM, BT, BG are the corresponding Jacobians that map them to the configuration space. Now let's start with designing the conjugate momentum based observer. We do this first by finding the estimated conjugate momentum term, which is nothing but the product of mass inertia and then the configuration velocity. Over here, hat represents the estimated value. Next, if we differentiate or take a time derivative of this conjugate momentum, we get the change in conjugate momentum, which is dependent on the acceleration and the change in mass inertia matrix. This change in mass inertia matrix is further numerically computed at every timestamp by performing backward-Euler differentiation. Next, if we use our full dynamical model that we obtained in the previous slide, which is a nonlinear dynamics of the system, and if we combine that with the time derivative of our conjugate momentum term, we get the observer dynamics. In this current observer dynamics, we don't have acceleration anymore. We only have the inputs, and we have the change in mass inertia matrix and in the combination of gravity and the Coriolis vector or the Coriolis matrix. All of this could be easily computed at every timestamp. So now we start with designing a filter for our estimator. We do so by considering the following filter design, where you take a difference of actual thrust of force and the estimated thrust of force and multiply that thing with a filter gain, that is K0. If we look at this particular filter in a frequency domain, we get the following transfer function, where T represents the time constant and it's equal to 1 upon K0, that is a filter gain. So if K0 tends to infinity, T tends to 0, and estimated thrust of force become equal to actual thrust of force. What this means is, in practical life, if we keep K0 high enough, then our estimated thrust of force will be equal to actual thrust of force. What this also shows or gives us is a stable, linearly decoupled first order filter for estimation. Next, if we take the observer dynamics obtained previously and combine that with the filter dynamics over here, then we get that our filter dynamics is nothing but the filter on a conjugate momentum term. And finally, if we integrate this following filter, we get our estimation at every timestamp using the following equation. Next, we find the ground reaction force using our contact model. The contact foot in the task space gives the following constraint, where Vf is the velocity for the contact foot and Af is the acceleration for the contact foot. We can rewrite this constraint in the generalized coordinate in the following form. Here, Jc denotes the contact foot Jacobian. Finally, given the contact constraint and the estimated thrust of force and the multimodal dynamics, we can estimate a contact force using the following equation. Over here, ampersand represents the pseudo-inverse. So, consider the robot model with three inputs, ut, ug, and um. Given the three input, it gives the generalized states and generalized velocity. Next, we add a momentum observer, which gives us thrust of force. The momentum observer is missing one input, that is the estimated ground reaction force, for which we add a contact model. And that completes our conjugate momentum observer design. This is the overall architecture that we follow for our estimator. Let me show you our results for the sensorless condition. The ground is modeled as a spring damper model. Plot shows the estimation of ground reaction force. Blue color shows the actual ground reaction force or the ground truth from the ground model, and the orange shows the estimate from the constraint model. Note, for Fx and Fy, the estimation is noisier. This is expected because it's sensorless. Fz, on the other hand, tracks reasonably well during the stance phase. Lastly, the ground model parameters are shown at the bottom over here. Next is the estimation for thrust of forces. We get GRF from the constraint model. Plot shows the estimation for thrust of force. Blue is the estimated one, and orange is the actual. Despite the noisier GRF estimate, thrust of force estimation is reasonable. Fx and Fy tracks actual force quite well. Fz shows some oscillation but captures the overall trend. Torque estimation is more challenging. Tx and Tz track reasonable, but Ty is significant error. This is due to the filter lag and the GRF estimation error propagation. The filter gains are set high in this. This is to compensate the error in the constraint model. Now we come to second case, which is the contact sensor case. In this, we assume that the force sensor is connected to the point of contact and gives the ground truth GRF. This dramatically increases the performance across all the axes. Force tracks almost perfectly with minimal lag. Notice the filter gains for this case is much more lower, that is just 25. Less aggressive filter needed when the ground direction force estimation is accurate. This validates that GRF accuracy is critical for thruster force estimation. In conclusion, this shows our method works excellent with force sensor and reasonably well even without them, making it practical for real robots. Finally, in conclusion, we provided a design for conjugate momentum based thruster force estimation. Due to estimator being a low-pass filter on observer dynamics, it highly depends on the ground reaction force. Next, we presented fairly accurate tracking results for both sensed and sensorless case. For future work, we want to improve the result and the accuracy. We can do this by performing a second order filter. Next is to test the estimator performance on actual Harpy hardware platform and to include the thruster dynamics to improve the estimator further. Thank you for listening.